Attention is all you need. Equal contribution. Listing order is random. Jakob proposed replacing RNNs with self-attention and started the effort to evaluate this idea. Ashish, with Illia, designed and implemented the first transformer models and has been crucially involved in every aspect of this work. Noam proposed scaled product attention, multi-head attention, and the parameter-free position representation and became the other person involved in nearly every detail. Niki designed, implemented, tuned, and evaluated countless model variants in our original codebase and Tensor-2 Tensor. Llion also experimented with novel model variants, was responsible for our initial codebase, and efficient inference and visualizations. Lukasz and Aidan spent countless long days designing various parts of and implementing Tensor-2 Tensor, replacing our earlier codebase, greatly improving results and massively accelerating our research. Work performed while at Google Brain, work performed while at Google Research. Abstract. The dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. The best performing models also connect the encoder and decoder through an attention mechanism. We propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. Experiments on 2 machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. Our model achieves 28.4 BLEU on the Walmart 2014 English to German translation task, improving over the existing best results, including ensembles, by over 2 BLEU. On the Walmart 2014 English to French translation task, our model establishes a new single model state-of-the-art BLEU score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training costs of the best models from the literature. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing both with large and limited training data. 1. Introduction. Recurrent neural networks, long short-term memory, 13, and gated recurrent, 7, neural networks in particular, have been firmly established as state-of-the-art approaches in sequence modeling and transduction problems such as language modeling and machine translation, 35, 2, 5. Numerous efforts have since continued to push the boundaries of recurrent language models and encoder-decoder architectures, 38, 24, 15. Recurrent models typically factor computation along the symbol positions of the input and output sequences. Aligning the positions to steps in computation time, they generate a sequence of hidden states ht, as a function of the previous hidden state ht-1 and the input for position t. This inherently sequential nature precludes parallelization within training examples, which becomes critical at longer sequence lengths, as memory constraints limit batching across examples. Recent work has achieved significant improvements in computational efficiency through factorization tricks, 21, and conditional computation, 32, while also improving model performance in case of the latter. The fundamental constraint of sequential computation, however, remains. Attention mechanisms have become an integral part of compelling sequence modeling and transduction models in various tasks, allowing modeling of dependencies without regard to their distance in the input or output sequences. 2, 19. In all but a few cases, 27, however, such attention mechanisms are used in conjunction with a recurrent network. In this work we propose the transformer, a model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly more parallelization and can reach a new state-of-the-art in translation quality after being trained for as little as 12 hours on 8P100 GPUs. 2. Background. The goal of reducing sequential computation also forms the foundation of the extended neural GPU, 16, ByteNet, 18, and CONVS2S, 9, all of which use convolutional neural networks as basic building block, computing hidden representations in parallel for all input and output positions. In these models, the number of operations required to relate signals from 2 arbitrary input or output positions grows in the distance between positions, linearly for CONVS2S and logarithmically for ByteNet. This makes it more difficult to learn dependencies between distant positions, 12. In the transformer this is reduced to a constant number of operations, albeit at the cost of reduced effective resolution due to averaging attention-weighted positions, an effect we counteract with multi-head attention as described in section 3.2. Self-attention, sometimes called interattention, is an attention mechanism relating different positions of a single sequence in order to compute a representation of the sequence. Self-attention has been used successfully in a variety of tasks including reading comprehension, abstractive summarization, textual entailment and learning task-independent sentence representations, 4, 27, 28, 22. End-to-end memory networks are based on a recurrent attention mechanism instead of sequence-aligned recurrence and have been shown to perform well on simple language question answering and language modeling tasks, 34. To the best of our knowledge, however, the transformer is the first transduction model relying entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolution. In the following sections, we will describe the transformer, motivate self-attention, and discuss its advantages over models such as 17, 18, and 9. 3. Model architecture. Figure 1, the transformer model architecture. Most competitive neural sequence transduction models have an encoder-decoder structure, 5, 2, 35. Here, the encoder maps an input sequence of symbol representations, x1, xn, to a sequence of continuous representations sadface z1, zn. Given, the decoder then generates an output sequence, y1, ym, of symbols one element at a time. At each step the model is autoregressive, 10, consuming the previously generated symbols as additional input when generating the next. The transformer follows this overall architecture using stacked self-attention and pointwise, fully connected layers for both the encoder and decoder, shown in the left and right halves of figure 1, respectively. 3.1 Encoder and decoder stacks. Encoder. The encoder is composed of a stack of n equals 6 identical layers. Each layer has two sublayers. The first is a multi-head self-attention mechanism, and the second is a simple, position-wise fully connected feed-forward network. We employ a residual connection, 11, around each of the two sublayers, followed by layer normalization, 1. That is, the output of each sublayer is layer norm x plus sublayer x, where sublayer x is the function implemented by the sublayer itself. To facilitate these residual connections, all sublayers in the model, as well as the embedding layers, produce outputs of dimensioned model equals 512. Decoder. The decoder is also composed of a stack of n equals 6 identical layers. In addition to the two sublayers in each encoder layer, the decoder inserts a third sublayer, which performs multi-head attention over the output of the encoder stack. Similar to the encoder, we employ residual connections around each of the sublayers, followed by layer normalization. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with fact that the output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I. 3.2 Attention. An attention function can be described as mapping a query and a set of key-value pairs to an output, where the query, keys, values, and output are all vectors. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. 3.2.1 Scaled.Product Attention. We call our particular attention Scaled.Product Attention, Figure 2. The input consists of queries and keys of dimension dk, and values of dimension dv. We compute the dot products of the query with all keys, divide each by dk, and apply a softmax function to obtain the weights on the values. In practice, we compute the attention function on a set of queries simultaneously, packed together into a matrix Q. The keys and values are also packed together into matrices K and V. We compute the matrix of outputs as attention Q K V equals softmax Q K T D K V. 1. The two most commonly used attention functions are additive attention, 2, and dot product, multiplicative attention. Dot product attention is identical to our algorithm, except for the scaling factor of 1 dk. Additive attention computes the compatibility function using a feed-forward network with a single hidden layer. While the two are similar in theoretical complexity, dot product attention is much faster and more space efficient in practice, since it can be implemented using highly optimized matrix multiplication code. While for small values of dk the two mechanisms perform similarly, additive attention outperforms dot product attention without scaling for larger values of dk. 3. We suspect that for large values of dk, the dot products grow large in magnitude, pushing the softmax function into regions where it has extremely small gradients. 11 To illustrate why the dot products get large, assume that the components of q and k are independent random variables with mean 0 and variance 1. Then their dot product, qk equals sigma I equals 1 key, has mean 0 and variance dk. To counteract this effect, we scale the dot products by 1 dk. 3.2.2 Multi-head attention. Scaled dot product attention. Multi-head attention. Figure 2, left, scaled dot product attention. Right, multi-head attention consists of several attention layers running in parallel. Instead of performing a single attention function with model dimensional keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values h times with different, learned linear projections to dk, and dv dimensions, respectively. On each of these projected versions of queries, keys, and values we then perform the attention function in parallel, yielding dv-dimensional output values. These are concatenated and once again projected, resulting in the final values, as depicted in Figure 2. Multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. With a single attention head, averaging inhibits this. Multi-head, Q, K, V. Equals concat, head 1, head, WO. Where heady. Equals attention, Q, YQ, K, WIC, V, with. Where the projections are parameter matrices YQ is an element temp model times DK, YK is an element temp model times DK, YV is an element temp model times DV, and WO is an element of HDV times model. In this work we employ H equals 8 parallel attention layers, or heads. For each of these we use DK equals DV equals model / H equals 64. Due to the reduced dimension of each head, the total computational cost is similar to that of single head attention with full dimensionality. 3.2.3 Applications of attention in our model. The transformer uses multi-head attention in 3 different ways. In encoder-decoder attention layers, the queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanisms in sequence-to-sequence models such as 38.2.9. The encoder contains self-attention layers. In a self-attention layer all of the keys, values, and queries come from the same place, in this case, the output of the previous layer in the encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder. Similarly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up to and including that position. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. We implement this inside of scaled.product attention by masking out, setting to -infinity, all values in the input of the softmax which correspond to illegal connections. See Figure 2. 3.3 Position-wise feed-forward networks. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network, which is applied to each position separately and identically. This consists of 2 linear transformations with a real U activation in between. FFN, x, equals max, 0, x w1 plus b1, w2 plus b2. 2. While the linear transformations are the same across different positions, they use different parameters from layer to layer. Another way of describing this is as two convolutions with kernel size 1. The dimensionality of input and output is model equals 512, and the inner layer has dimensionality DFF equals 2048. 3.4 Embeddings and softmax. Similarly to other sequence transduction models, we use learned embeddings to convert the input tokens and output tokens to vectors of dimensioned model. We also use the usual learned linear transformation and softmax function to convert the decoder output to predicted next token probabilities. In our model, we share the same weight matrix between the two embedding layers and the pre-softmax linear transformation, similar to 30. In the embedding layers, we multiply those weights by model. 3.5 Positional encoding. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence. To this end, we add positional encodings to the input embeddings at the bottoms of the encoder and decoder stacks. The positional encodings have the same dimensioned model as the embeddings, so that the two can be summed. There are many choices of positional encodings, learned and fixed. 9. In this work, we use sine and cosine functions of different frequencies. PE, POS 2I, equals SIN, POS slash 1000002I slash model. PE, POS 2I plus 1, equals COS, POS slash 1000002I slash model. Where POS is the position and I is the dimension. That is, each dimension of the positional encoding corresponds to a sinusoid. The wavelengths form a geometric progression from 2 pi to 1000002 pi. We chose this function because we hypothesized it would allow the model to easily learn to attend by relative positions, since for any fixed offset k, PEPOS plus k can be represented as a linear function of PEPOS. We also experimented with using learned positional embeddings, 9, instead, and found that the two versions produced nearly identical results, see table 3 row, E. We chose the sinusoidal version because it may allow the model to extrapolate to sequence lengths longer than the ones encountered during training. For why self-attention? In this section we compare various aspects of self-attention layers to the recurrent and convolutional layers commonly used for mapping one variable length sequence of symbol representations, x1, xn, to another sequence of equal length, z1, zn, with 11z as an element of d, such as a hidden layer in a typical sequence transduction encoder or decoder. Motivating our use of self-attention we consider three desiderata. One is the total computational complexity per layer. Another is the amount of computation that can be parallelized, as measured by the minimum number of sequential operations required. The third is the path length between long-range dependencies in the network. Learning long-range dependencies is a key challenge in many sequence transduction tasks. One key factor affecting the ability to learn such dependencies is the length of the paths forward and backward signals have to traverse in the network. The shorter these paths between any combination of positions in the input and output sequences, the easier it is to learn long-range dependencies. 12. Hence we also compare the maximum path length between any two input and output positions in networks composed of the different layer types. Table 1, maximum path lengths, per layer complexity, and minimum number of sequential operations for different layer types. N is the sequence length, D is the representation dimension, K is the kernel size of convolutions and are the size of the neighborhood in restricted self-attention. O, R and D. O, 1. O, N/R. As noted in Table 1, a self-attention layer connects all positions with a constant number of sequentially executed operations, whereas a recurrent layer requires O, N, sequential operations. In terms of computational complexity, self-attention layers are faster than recurrent layers when the sequence length n is smaller than the representation dimensionality d, which is most often the case with sentence representations used by state-of-the-art models in machine translations, such as wordpiece, 38, and byte pair, 31, representations. To improve computational performance for tasks involving very long sequences, self-attention could be restricted to considering only a neighborhood of size r in the input sequence centered around the respective output position. This would increase the maximum path length to O, N/R. We plan to investigate this approach further in future work. A single convolutional layer with kernel width k less than n does not connect all pairs of input and output positions. Doing so requires a stack of O, N/K, convolutional layers in the case of contiguous kernels, or O, LOGK, N, in the case of dilated convolutions, 18, increasing the length of the longest paths between any two positions in the network. Convolutional layers are generally more expensive than recurrent layers, by a factor of k separable convolutions, 6, however, decrease the complexity considerably, to O, K and D plus ND2. Even with k equals n, however, the complexity of a separable convolution is equal to the combination of a self-attention layer and a pointwise feed-forward layer, the approach we take in our model. As side benefit, self-attention could yield more interpretable models. We inspect attention distributions from our models and present and discuss examples in the appendix. Not only do individual attention heads clearly learn to perform different tasks, many appear to exhibit behavior related to the syntactic and semantic structure of the sentences. 5. Training. This section describes the training regime for our models. 5.1 Training data and batching. We trained on the standard Walmart 2014 English-German dataset consisting of about 4.5 million sentence pairs. Sentences were encoded using byte pair encoding, 3, which has a shared source target vocabulary of about 37,000 tokens. For English-French, we used the significantly larger Walmart 2014 English-French dataset consisting of 36M sentences and split tokens into a 32,000 word piece vocabulary, 38. Sentence pairs were batched together by approximate sequence length. Each training batch contained a set of sentence pairs containing approximately 25,000 source tokens and 25,000 target tokens. 5.2 Hardware and schedule. We trained our models on one machine with 8 NVIDIA P100 GPUs. For our base models using the hyperparameters described throughout the paper, each training step took about 0.4 seconds. We trained the base models for a total of 100,000 steps or 12 hours. For our big models, described on the bottom line of Table 3, step time was 1 second. The big models were trained for 300,000 steps, 3.5 days. 5.3 Optimizer. We used the Atom Optimizer, 20, with beta 1 equals 0.9, beta 2 equals 0.98 and epsilon equals 10-9. We varied the learning rate over the course of training, according to the formula. LRATE equals model minus 0.5 min, STEP underscore NUM minus 0.5 STEP underscore NUMWAR MUP underscore STEPS minus 1.5. 3. This corresponds to increasing the learning rate linearly for the first WAR MUP underscore STEPS training steps, and decreasing it thereafter proportionally to the inverse square root of the step number. We used WAR MUP underscore STEPS equals 4000. 5.4 Regularization. We employ 3 types of regularization during training. Residual dropout. We apply dropout, 33, to the output of each sublayer, before it is added to the sublayer input and normalized. In addition, we apply dropout to the sums of the embeddings and the positional encodings in both the encoder and decoder stacks. For the base model, we use a rate of PD or OP equals 0.1. Label smoothing. During training, we employed label smoothing of value LS equals 0.1, 36. This hurts perplexity, as the model learns to be more unsure, but improves accuracy and BLU score. 6 results. 6.1 Machine translation. Table 2, the transformer achieves better BLU scores than previous state-of-the-art models on the English to German and English to French News Test 2014 tests at a fraction of the training cost. On the Walmart 2014 English to German translation task, the big transformer model, transformer, big, in Table 2, outperforms the best previously reported models, including ensembles, by more than 2.0 BLU, establishing a new state-of-the-art BLU score of 28.4. The configuration of this model is listed in the bottom line of Table 3. Training took 3.5 days on 8 P100 GPUs. Even our base model surpasses all previously published models and ensembles, at a fraction of the training cost of any of the competitive models. On the Walmart 2014 English to French translation task, our big model achieves a BLU score of 41.0, outperforming all of the previously published single models, at less than 1/4 the training cost of the previous state-of-the-art model. The transformer, big, model trained for English to French used dropout rate PD or OP equals 0.1, instead of 0.3. For the base models, we used a single model obtained by averaging the last 5 checkpoints, which were written at 10-minute intervals. For the big models, we averaged the last 20 checkpoints. We used beam search with a beam size of 4 and length penalty alpha equals 0.6, 38. These hyperparameters were chosen after experimentation on the development set. We set the maximum output length during inference to input length plus 50, but terminate early when possible, 38. Table 2 summarizes our results and compares our translation quality and training costs to other model architectures from the literature. We estimate the number of floating point operations used to train a model by multiplying the training time, the number of GPUs used, and an estimate of the sustained single precision floating point capacity of each GPU. 22 We used values of 2.8, 3.7, 6.0, and 9.5 teraflops for K80, K40, M40 and P100, respectively. 6.2 Model variations. Table 3, variations on the transformer architecture. Unlisted values are identical to those of the base model. All metrics are on the English to German translation development set, News Test 2013. Listed perplexities are per word piece, according to our byte pair encoding, and should not be compared to per word perplexities. N. Model. To evaluate the importance of different components of the transformer, we varied our base model in different ways, measuring the change in performance on English to German translation on the development set, News Test 2013. We used beam search as described in the previous section, but no checkpoint averaging. We present these results in Table 3. In Table 3 rows, A, we vary the number of attention heads and the attention key and value dimensions, keeping the amount of computation constant, as described in section 3.2.2. While single head attention is 0.9 BLU worse than the best setting, quality also drops off with too many heads. In Table 3 rows, B, we observe that reducing the attention key size decay hurts model quality. This suggests that determining compatibility is not easy and that a more sophisticated compatibility function than dot product may be beneficial. We further observe in rows C and D that, as expected, bigger models are better, and dropout is very helpful in avoiding overfitting. In row E, we replace our sinusoidal positional encoding with learned positional embeddings, 9, and observe nearly identical results to the base model. 6.3 English constituency parsing. Table 4, the transformer generalizes well to English constituency parsing. Results are on section 23 of Wall Street Journal. To evaluate if the transformer can generalize to other tasks, we performed experiments on English constituency parsing. This task presents specific challenges. The output is subject to strong structural constraints and is significantly longer than the input. Furthermore, RNN sequence-to-sequence models have not been able to attain state-of-the-art results in small data regimes, 37. We trained a 4-layer transformer with DMODEL equals 1024 on the Wall Street Journal, portion of the Penn Tree Bank, 25, about 40K training sentences. We also trained it in a semi-supervised setting, using the larger high-confidence and Berkeley parser corpora from with approximately 17M sentences, 37. We used a vocabulary of 16K tokens for the Wall Street Journal only setting and a vocabulary of 32K tokens for the semi-supervised setting. We performed only a small number of experiments to select the dropout, both attention and residual, section 5.4, learning rates and beam size on the section 22 development set. All other parameters remained unchanged from the English to German base translation model. During inference, we increased the maximum output length to input length plus 300. We used a beam size of 21 and alpha equals 0.3 for both Wall Street Journal only and the semi-supervised setting. Our results in Table 4 show that despite the lack of task-specific tuning, our model performs surprisingly well, yielding better results than all previously reported models with the exception of the recurrent neural network grammar, 8. In contrast to RNN sequence-to-sequence models, 37, the transformer outperforms the Berkeley parser, 29, even when training only on the Wall Street Journal training set of 40K sentences. 7. Conclusion. In this work, we presented the transformer, the first sequence transduction model based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-headed self-attention. For translation tasks, the transformer can be trained significantly faster than architectures based on recurrent or convolutional layers. On both Walmart 2014 English to German and Walmart 2014 English to French translation tasks, we achieve a new state of the art. In the former task, our best model outperforms even all previously reported ensembles. We are excited about the future of attention-based models and plan to apply them to other tasks. We plan to extend the transformer to problems involving input and output modalities other than text and to investigate local, restricted attention mechanisms to efficiently handle large inputs and outputs such as images, audio and video. Making generation less sequential is another research goal of ours. The code we use to train and evaluate our models is available at https://github.com/tensorflow/tensor2tensor. Acknowledgements. We are grateful to NAL Couchbrenner and Stefan Gauss for their fruitful comments, corrections, and inspiration. References. 1. Jimmy Leybaugh, Jamie Ryan Quiros, and Jeffrey E. Hinton. Layer normalization. AR14 preprint AR14, 1607.06450, 2016. 2. Dmitry Bodanow, Kyunghyun Cho, and Yoshua Benjo. Neural machine translation by jointly learning to align and translate. CORR, AB/1409.0473, 2014. 3. Denny Britz, Anna Goldie, Mintang Luong, and Kwok V. Liu. Massive exploration of neural machine translation architectures. CORR, AB/1703.03906, 2017. 4. Jianpeng Ching, Li Dong, and Mirella Lapada. Long short-term memory networks for machine reading. AR14 preprint AR14, 1601.06733, 2016. 5. Kyunghyun Cho, Bart van Marienboer, Keller Gulser, Fethi Bugers, Holger Schwenk, and Yoshua Benjo. Learning phrase representations using RNN encoder-decoder for statistical machine translation. CORR, AB/1406.1078, 2014. 6. François Chalet. Seption, Deep Learning with Depthwise Separable Convolutions. AR14 preprint AR14, 1610.02357, 2016. 7. Jinyang Chung, Keller Gulser, Kyunghyun Cho, and Yoshua Benjo. Empirical Evaluation of Gated Recurrent Neural Networks on Sequence Modeling. CORR, AB/1412.3555, 2014. 8. Chris Dyer, Adhigana Kunkoro, Miguel Ballesteros, and Noah A. Smith. Recurrent Neural Network Grammars. In Proc of NAACL, 2016. 9. Jonas Gehring, Michael Ollie, David Grangier, Dennis Yaretz, and Jan N. Dauphin. Convolutional Sequence-to-Sequence Learning. AR14 preprint AR14, 1705.03122v2, 2017. 10. Alex Graves. Generating Sequences with Recurrent Neural Networks. AR14 preprint AR14, 1308.0850, 2013. 11. Kaiming He, Xiangyu Zhang, Xiaoqing Ren, and Jian Sunday. Deep Residual Learning for Image Recognition. In Proceedings of the IEEE Conference on Computer Vision and Pattern Recognition, pages 770 to 778, 2016. 12. Sepp Hochreiter, Yoshua Benjo, Paolo Fresconi, and Jürgen Schmidt-Huber. Gradient Flow in Recurrent Nets, The Difficulty of Learning Long-Term Dependencies, 2001. 13. Sepp Hochreiter and Jürgen Schmidt-Huber. Long Short-Term Memory. Neural Computation, 9, 8-1735, 1780, 1997. 14. Zhongcheng Huang and Mary Harper. Self-Training PCFG Grammars with Latent Annotations Across Languages. In Proceedings of the 2009 Conference on Empirical Methods in Natural Language Processing, pages 832 to 841. ACL, August 2009. 15. Rafal Josefovich, Oriol Vinyals, Mike Schuster, Noam Shazeer, and Yonghui Wu. Exploring the Limits of Language Modeling. AR14 preprint AR14, 1602.02410, 2016. 16. Lukasz Kaiser and Sami Benjo. Can Active Memory Replace Attention? In Advances in Neural Information Processing Systems, NIPS, 2016. 17. Lukasz Kaiser and Illia Polosukhin. Neural GPUs Learn Algorithms. In International Conference on Learning Representations, ICLR, 2016. 18. NAL Couchbrenner, Lasse Espolt, Karen Simonian, Aaron van den Ord, Alex Graves, and Kore Kavachuoglu. Neural machine translation in linear time. AR14 preprint AR14 1610.10099v2, 2017. 19. Yoon Kim, Carl Denton, Luong Hong, and Alexander M. Rush. Structured Attention Networks. An International Conference on Learning Representations, 2017. 20. Diederik Kingma and Jimmy Ba. Atom, a method for stochastic optimization. In ICLR, 2015. 21. Alexei Kucheyev and Boris Ginsburg. Factorization tricks for LSTM networks. AR14 preprint AR14 1703.10722, 2017. 22. Johan Lin, Minwei Feng, Cicero Nogueira dos Santos, MOU, Bing Xiong, Bowen Zhou, and Yoshua Benjo. A structured self-attentive sentence embedding. AR14 preprint AR14 1703.03130, 2017. 23. Mintang Luong, Kwok V. Liu, Illia Polosukhin, Oriol Vinyals, and Lukasz Kaiser. Multitask sequence-to-sequence learning. AR14 preprint AR14 1511.06114, 2015. 24. Mintang Luong, Hugh Pham, and Christopher D. Manning. Effective approaches to attention-based neural machine translation. AR14 preprint AR14 1508.04025, 2015. 25. Mitchell P. Marcus, Marianne Marcinkiewicz, and Beatrice Santorini. Building a large annotated corpus of English, the Penn Tree Bank. Computational Linguistics, 19, 2313, 330, 1993. 26. David McCloskey, Eugene Charniak, and Mark Johnson. Effective self-training for parsing. In Proceedings of the Human Language Technology Conference of the NAACL, Main Conference, pages 152 to 159. ACL, June 2006. 27. Ankur Parikh, Oscar Tackstrom, Dipanjan Das, and Jakob Uszkoreit. A decomposable attention model. In Empirical Methods in Natural Language Processing, 2016. 28. Romain Paulus, Kaiming Xiong, and Richard Socher. A deep reinforced model for abstractive summarization. AR14 preprint AR14 1705.04304, 2017. 29. Slav Petrov, Leon Barrett, Romain Thibox, and Dan Klein. Learning accurate, compact, and interpretable tree annotation. In Proceedings of the 21st International Conference on Computational Linguistics and 44th Annual Meeting of the ACL, pages 433 to 440. ACL, July 2006. 30. Ophir Press and Lior Wolf. Using the output embedding to improve language models. AR14 preprint AR14 1608.05859, 2016. 31. Rico Senrich, Barry Haddo, and Alexander Birch. Neural machine translation of rare words with subword units. AR14 preprint AR14 1508.07909, 2015. 32. Noam Shazeer, Azalea Mirasini, Christoph Maziars, Andy Davis, Kwok Liu, Jeffrey Hinton, and Jeff Dean. Outrageously large neural networks, the sparsely gated mixture of experts layer. AR14 preprint AR14 1701.06538, 2017. 33. Niti Shrivastava, Jeffrey E. Hinton, Alex Krashevsky, Ilya Polosukhin, and Ruslan Salakutinov. Dropout, a simple way to prevent neural networks from overfitting. Journal of Machine Learning Research, 15, 1 1929-1958, 2014. 34. Sangbayer Sukbader, Arthur Slom, Jason Weston, and Rob Fergus. End-to-end memory networks. In C. Cortez, N. D. Lawrence, D. D. Lee, M. Sugiyama, and R. Garnett, editors, Advances in Neural Information Processing Systems 28, pages 2440 to 2448. Curran Associates Incorporated, 2015. 35. Illia Polosukhin, Oriol Vinyals, and Kwok V. Liu. Sequence-to-sequence learning with neural networks. In Advances in Neural Information Processing Systems, pages 3104 to 3112, 2014. 36. Christian Szegedy, Vincent Van Houk, Sergey Yaffe, Jonathan Schlenz, and Zbigniew Wojna. Rethinking the Inception Architecture for Computer Vision. CORR, AB/1512.00567, 2015. 37. Vinyals and Kaiser, Ku, Petrov, Polosukhin, and Hinton. Grammar as a Foreign Language. In Advances in Neural Information Processing Systems, 2015. 38. Yonghui Wu, Mike Schuster, Jifeng Chen, Kwok V. Liu, Mohammad Narouzi, Wolfgang Masheri, Maxim Krikin, Yuan Chao, Qin Gao, Klaus Masheri, et al. Google's Neural Machine Translation System, bridging the gap between human and machine translation. AR14 preprint AR14 1609.08144, 2016. 39. Jie Zhou, Ying Chao, Xuguang Wang, Peng Li, and Wei Su. Deep recurrent models with fast-forward connections for neural machine translation. CORR, AB/1606.04199, 2016. 40. Muhua Zhu, Yu Zhang, Wenliang Chen, Min Zhang, and Jingguo Zhu. Fast and accurate shift-reduce constituent parsing. In Proceedings of the 51st Annual Meeting of the ACL, Volume 1, Long Papers, pages 434 to 443. ACL, August 2013. Attention visualizations. Figure 3, an example of the attention mechanism following long-distance dependencies in the encoder self-attention in layer 5 of 6. Many of the attention heads attend to a distant dependency of the verb making, completing the phrase making more difficult. Attentions here shown only for the word making. Different colors represent different heads. Best viewed in color. Figure 4, 2 attention heads, also in layer 5 of 6, apparently involved in an AFR resolution. Top, full attentions for head 5. Bottom, isolated attentions from just the word. Its 4 attention heads 5 and 6. Note that the attentions are very sharp for this word. Figure 5, many of the attention heads exhibit behavior that seems related to the structure of the sentence. We give 2 such examples above, from 2 different heads from the encoder self-attention at layer 5 of 6. The heads clearly learn to perform different tasks. Report issue. Generated by LATEXML. Instructions for reporting errors. We are continuing to improve HTML versions of papers, and your feedback helps enhance accessibility and mobile support. To report errors in the HTML that will help us improve conversion and rendering, choose any of the methods listed below. Click the Report Issue button. Open a report feedback form via keyboard, use Ctrl+?. Make a text selection and click the Report Issue for Selection button near your cursor. Our team has already identified the following issues. We appreciate your time reviewing and reporting rendering errors we may not have found yet. Your efforts will help us improve the HTML versions for all readers, because disability should not be a barrier to accessing research. Thank you for your continued support in championing open access for all. Have a free development cycle? Help support accessibility at AR14. Our collaborators at LaTeXML maintain a list of packages that need conversion and welcome developer contributions.